Let's start.
All right. Assalamu alaikum, everyone. I hope you're all doing well. Thank you all for joining us today. My name is Iman Ahmed, and I'm a third-year medical student at the FMH College of Medicine and Dentistry. I'm a core team member at the Center of Health Sciences Research, which is a research platform at FMH, and I am also part of the organizing committee for this webinar series. Welcome to our third session. The topic for today's session is inferential statistics, and the panelist for today is joining us from the UK, Dr. Ahmed Waqas. Dr. Ahmed Waqas currently works as a postdoctoral research associate at the Institute of Population Health at the University of Liverpool in the UK. He is a public mental health physician who advocates for equal access to mental health care for life communities. He is also involved in designing digital health intervention application for personalized mental health care in low resource settings, which has also been tested in Pakistan. Additionally, Dr. with global health organizations, including the World Health Organization, on perinatal mental health policies and guidelines on maternal mental disorders. For his work, he has been recognized as Dr. Paramjit Kaur Joshi Research Scholar for his contributions to child and adolescent mental health in Pakistan. Dr. Ahmed has over 100 peer-reviewed publications and an age index of 25, influencing the mental health sector. Today, he will be teaching us about statistics and we'll be talking on inferential statistics. Over to you, Dr. Ahmed.
Thank you for introducing me, Iman. I'll just give a brief introduction of myself. So I'm Ahmed Waqas. I am a medic by background. I had completed my MBBS in Pakistan back in 2016, and I completed my PhD in psychiatry last year from the University of Liverpool School of Medicine. And currently I'm working as a postdoctoral fellow at the University of Liverpool in the same department. And I also lead the evidence synthesis department at the Mercer NHS Foundation Trust, where we try to generate evidence-based psychiatric approaches to be used by the doctors in Liverpool and the surrounding region. So today, although during the introduction, the topic introduced is on inferential statistics, it is quite a large topic and it's impossible to cover it within 90 minutes. So what we are going to do is we're going to focus on correlation and regression analysis, which are two very critical statistical concepts in inferential statistics. These two principles are the backbone of many medical research studies. And by the end of this research presentation, you will hopefully have a better understanding of how these tools and statistical concepts can help us make predictions, establish relationships, and improve patient care. And although it is going to be a very superficial exploration of these two topics, the reason being that it is designed as an applied epidemiology module for junior doctors. When you graduate from medicine and go for more advanced degrees, such as Masters in Public Health and PhD, hopefully you would be able to explore these in further detail. So the structure of the lecture today would be that in the first 20 minutes, we are going to go through the assumptions that I have regarding the participants of this lecture. So I do assume that you have some basic knowledge regarding medical statistics, which you may have gained through undergraduate level courses in stats. Then we will talk about correlation, the limitations of correlation, and then we will touch upon the concept of confounding. After that, we'll have a 10-minute break, followed by a detailed discussion on regression analysis, detailed discussion on its assumptions. We will explore some critical concepts that are needed before running regression analysis. And then we will have a demonstration of these correlation and regression analysis in SPSS followed by interpretation of the output that is generated by the software. After that, we will have a 15-minute break, which will be followed by a 30-minute discussion on the topic. So I do assume that the participants have some previous knowledge of medical statistics, and this could have been obtained through undergraduate level stats teaching that's done in the subject of community medicine, both in MBBS and PDS degrees. And I do hope that all of you have a good grasp on the following concepts: type of variables, concept of central tendency and dispersion, normal versus non-normal distribution, p-values, confidence intervals, type 1, type 2 errors, concept of statistical power, and understanding of how to run some basic statistical tests such as independent sample t-test, chi-square analysis, and their corresponding non-parametric statistical test in SPSS or any other statistical package. I do hope or assume that you would have some knowledge of the concept of confounding, what is correlation and what is causality. I would hope that you have some grasp on study designs as well, that you can appreciate cross-sectional research, case control studies, longitudinal studies, and experimental studies. And you do have some knowledge of the biases that exist in medical research. So the next of the slides, although basic, they do build upon all of these concepts. Now, let us begin with what is correlation. And while going through research papers, you may have heard about or read about correlation, right? That variable A correlates with variable B. For instance, in a recent paper, I read a sentence that said, studies have found a strong positive correlation between age and heart disease. So what does this mean? This simply means that as age increases, so does the likelihood of heart disease, right? So this is an application of correlation, and you do come across such sentences in almost any medical research paper. Now, let us begin with a very specific statistical technique for assessing correlation between two variables. And we will begin with a very detailed case study, which assessed the relationship between body mass index and systolic blood pressure. So a group of medical researchers, they wanted to determine if there is a relationship between body mass index and systolic blood pressure in adults. So what they do is they run a cross-sectional study. They gathered data from a sample of 200 adult patients. The data included BMI scores and systolic blood pressure readings. They input this data in SPSS and they run a Pearson correlation analysis and find that the correlation coefficient R is equal to 0.65, right? And they report these findings in their research paper, and in the limitation section, they report that the results of this study should be interpreted with caution because correlation does not imply causation. Now, what do we make of this case study? Number one, they run a cross-sectional study, right? Number two, they conducted a Pearson correlation coefficient, and the result is represented by a correlation coefficient of R equals 0.65. And in the limitation section, they caution that it is correlation and not causation. So firstly, the result for this correlation coefficient, it suggests that there is a strong positive relationship between the BMI and the systolic blood pressure. So as the BMI increases, so does the systolic blood pressure, right? You may infer from it or deduce from it that high BMI could be associated with a higher risk of hypertension, right? And that supports previous research findings. But when the researchers caution that the correlation does not imply causation, That just means that there may be other confounding factors involved, such as diet, physical activity, affecting both BMI and blood pressure. Moreover, the association might not be linear across the entire range of BMI score. So for instance, the association between BMI and systolic blood pressure might differ for people who have very low BMI compared to people who have very high BMI, right? So just by looking at the study design and the analysis that they have run, you can deduce so many things. Now, along with the previous results or previous sentences, the authors may also report a scatter plot, right? Now, what does the scatter plot mean? This is the x-axis and this is the y-axis, right? On the x-axis, they have the BMI, the body mass index, and on the y-axis, they have a systolic blood pressure. And within this scatter plot, you see these points, right? So these individual points are actually individual data points, data for individual study participants. So for this level of BMI, right, this would be the level for the systolic blood pressure. So they plot all the data points on a scatter plot, right? And they fit a line of it or a regression line, which is as BMI increases, the systolic blood pressure increases. So this shows a strong positive correlation between the BMI and blood pressure. So how do we interpret this Pearson correlation coefficient? Right? So correlation can be both positive, where both variables increase, as in previous slide, or it could be negative, where when one variable increases, the other will decrease, or it could be zero, corresponding to no relationship at all. Now, the value of R gives us two important pointers or considerations. Firstly, it shows us the strength of the association. Are two variables weakly correlated or strongly correlated, or are they not correlated at all? And then it also shows us the direction of linear relationship, if it is positive, negative, or zero, right? So in medical research, a strong correlation could suggest a strong association between two health-related factors. And there are a few guidelines, such as the Cohen's guidelines, which can be used to interpret the strength of the effect size of the correlation coefficient R. If R is equal to 0.10, it corresponds to a small effect size or weak association. If R is equal to 0.35 or 0.30, or between 0.3 to 0.5, it would be a medium effect size. And anything in R equal to 0.5 and greater would correspond to a large effect size or a very strong association, right? So we're not really going in a lot of detail related to the scientific or mathematical notation or the formula for the Spearman or the Pearson correlation here, just to keep things simple. Now let's look at case study B. In the previous case studies, we saw that we had two variables, BMI, which is a continuous variable, and a systolic blood pressure, which is also a continuous variable. So what Pearson correlation analysis does is it assesses the relationship between two continuous variables. But what if one of the variables is not continuous? It is ordinal, right? It is divided into ordered categories, like you see in a Likert scale response system, right? Or A of study 1, 2, 3, 4, 5. Variable that has a natural order. Then for that, we run Spearman correlation, right? So just as a case study, we'll talk about a recent study that was done. It is a fictitious study that a clinical trial was conducted to assess the severity of symptoms in patients with a chronic illness before and after a new treatment. The symptoms were assessed using a questionnaire, right? Severity of symptoms was assessed using a questionnaire, and the patient's responses were ranked, right? That they may have ranked the symptoms from no symptoms at all to moderate symptoms, some symptoms, strong or severe symptoms, right? So for this sort of data, where one or both of the variables are ordinal, you use Spearman correlation to determine whether there was a significant relationship between the rankings of symptom severity before and after treatment, just as in this case study. Now, Spearman correlation is also known as Spearman's rank correlation coefficient. And just like the Pearson correlation, it measures the strength and direction of the relationship, right? Now, there is one important concept here of monotonic relationship, right? So what does monotonic relationship mean? It means that as the value of one variable increases, so will the value of the other variable, right? So both the variables should be in an increasing order, right? As the value of one variable increases, the value of other variable decreases. So it could be in either direction, but it has to be monotonic, right? So the Pearson correlation, it assesses linear relationship, just like shown in that scatter plot. The Spearman correlation assesses monotonic relationships, right? Whether linear or not. So when you, so this is a graph that was taken from this particular study, right? Which compares monotonic relationship and non-monotonic relationship. What it does is it these are scatter plots that compare or relate dose of a drug with response generated, right? So this is a linear relationship, right? And it is quite monotonic, that as the dose increases, the response to the drug will increase as well, right? But here are the examples of non-monotonic relationship. So if you run a scatter plot, and this is something that you see, that the relationship between dose and response is biphasic, or it is a U-shaped, right? Or it is inverted U-shaped. Now these are non-monotonic relationships. You cannot assess these using a Spearman correlation, right? You can only assess the relationship between two variables when they are related to each other in a monotonic manner. Now, I will, when we run the SPSS demonstration, I will take you through all of these terminologies and how you can interpret them, right? So what are the limitations of correlation? Number one, as we saw in the previous case study, the researchers cautioned that correlation does not mean causation, right? And then there's a concept of random coincidence or spurious correlation as well. It is a very common terminology used in medical and public health research. So for instance, let's talk about the first limitation of random coincidence, also known as spurious correlation, right? And a very good example for this to demonstrate this sort of limitation is a study that was called that led to formulation of the Redskins rule. So it was a study that showed that that the football team's record of winning in the US, right, was correlated with presidential election. So what happened was that in the Redskins rule, the result of the last game of the Washington football team before the US presidential elections accurately predicted every election result from 1936 to 2000. So people may assume that the outcome of the football game was somehow related to the presidential elections, right? But this observation was just a coincidence, right? And we call it random coincidence or a spurious correlation, right? And in a data set, the more correlation analysis you run, if you have 100 variables and you try to correlate them using a Pearson correlation or Spearman correlation coefficient, you may come across statistically significant results, right? Even though in reality, those variables are unrelated. And then there is an important limitation of reverse causality, right? That using these correlation analysis, you cannot really determine the direction of association, right? Or you cannot really determine if the relationship is causal. So for instance, if you say that uh, the strength of the wind was correlated with the number of revolutions that were done by a spinning windmill, right? So that is what the correlation will say. It will just talk about correlate or association. It will not tell you that if it was the wind that was driving the spinning windmill, or was it the windmill that was leading to the wind being more ferocious and more intense, right? So this concept of reverse causality is really important. Another important example of spurious correlations is this particular graph that showed that the divorce rate in Maine, the state of Maine in the US, correlated with the per capita consumption of margarine, right? So you would see here that this red line corresponds to, or these data points correspond to divorce rate in Maine, and the margarine, the volume of margarine consumed corresponds to this black line and these black data points, right? So as the volume of margarine consumed reduced, so did the divorce rate in Maine, right? You see a dip here and you see a dip here as well, and you see that the direction is similar for both of the lines, right? Of both the data points. So again, there is no logical sense to it, and these are just spurious correlations. And you do see in a lot of studies that there is a table of correlations in those studies, right? Where you have multiple variables that have been correlated, and we do not really try to warn the participants or the readers that these relationships could be spurious. And there may be a lot of confounding involved. Now, this concept of confounding variable, it is really important as well. A study was published that showed that alcohol consumption was associated with lung cancer. The more the alcohol consumed, the higher the likelihood of developing lung cancer in patients, right? But then in subsequent studies, epidemiologists tried to elucidate that smoking was a confounder in this relationship, right? Now, what does this mean? That it is not the association between alcohol consumption and lung cancer. These are not really correlated, right? What they elucidate was that smoking, the people who smoke also have higher alcohol consumption, right? So it is not really the alcohol consumption that is increasing the likelihood of lung cancer, it is actually smoking. So this middle variable here is the confounding variable that is kind of driving an increase in both the variables or both the events of alcohol consumption and lung cancer. So understanding this is really important, right? So when we say that that divorce rate in Maine correlates with per capita consumption of margarine, that's not the case. It is spurious, and there may be some confounding factors involved, or there is a hidden variable that's driving this correlation, right? Now, we will just take a small break of 10 minutes here, and we can have some questions before we move on to the regression analysis. So I'll just open up the chat box. So there are quite a few questions here. Okay. So the question is, how do we know where to use what kind of relationship? So Abdullah, can you please elaborate this question? I couldn't understand the question. How do we know where to use what kind of relationship? So what I think what you mean is that how do we know if the relationship is positive or negative, right? So you just look at the value of R, or correlation coefficient. If it is, yes. So if the value of R is positive, it means the relationship is positive. That if one variable increases, the other will increase as well. And if the correlation coefficient R is negative, then that just means that there is an inverse relationship. That if the value of one variable increases, the value of the other, the second variable, decreases. And the next question is by Dua, which is, could you please explain again the difference between Pearson and Spearman correlation? So Pearson is for two variables that are both continuous, right? And Spearman correlation is for variables that are ordinal in nature, that have ordered categories. So example of continuous variable would be BMI. It can range from 0 to any value really, and it has decimal points as well, right? So it's a continuous variable. And regarding the Spearman, Spearman correlation is for ordinal variables, right? So ordinal variable would be something like year of study, year 1, year 2, year 3, year 4, year 5, right? Or it could be a Likert scale response that says slightly agree, not agreed, neutral, agree, highly agree. So that's an ordinal variable as well. Now, Rija is asking, how do we determine whether or not an effect is caused by confounders, right? So this is a very important question. And this would really be explained by two things. Number one, that you can determine this. So for instance, if you're trying to correlate two variables, right? So what would happen is that you may get a spurious correlation, that they are positively correlated. But how would we know that this effect is caused by confounders? So for instance, number one would be logical sense. Number two would be that that you read previous literature and you see that in previous literature, the correlation is being, can be explained by a confounder variable, or they are showing some sort of other associations with other variables, right? So that could be one thing. And then you can also explore it through your data set if it is extensive enough. And we will talk about it later on, that how you can use stratification, how you can use regression analysis to account for this or to identify this confounding effect of a variable. There is a Dr. Naveed, there's a WhatsApp image, but it's a file. It's asking me to download it. Is it a question or?
No, it's just a resource. So, when to use Pearson correlation, when to use Spearman, when to use t-test.
Yes.
or SIG rank test. So, I just wanted to explain that if your data is normal versus your data is not normal, just normally distributed, then based on the variables that you have, you can run all these tests based on data normality and what kind of variables are you assessing for.
So all of this knowledge that I have shared, right, it was based on the assumption that you already know these things, the participants know these things, and it's just a sort of a revision or a small primer of these concepts, right? So that is why I did not go into a lot of detail on how to look for normality and meet the assumptions for Pearson correlation. But we did talk about linearity, that it looks for linear relationship alone. And that could be seen in the scatter plot. Again, just like this scatter plot, this relationship is linear and this can be tested by Pearson correlation as well. And if both the variables, one of the variable was ordinal, let's say low, no dose at all, high dose, very high dose, that would be ordinal, right? You would test this linear relationship using Spearman correlation.
So Dr. Vikas, is it possible if I share that screenshot and you can briefly go over that, because we had to cancel one or postpone one lecture?
Yeah.
If I share that screenshot, you can briefly go over that.
Yes, of course, yeah.
I think that would be very helpful for the participants.
Yeah.
So I think on the top, if your assumption is that your data is normally distributed, on the bottom, if your data is not normally distributed. So can you explain that a little bit?
So the upper row of the test, that just show the statistical tests, right? That could be run when the data is normal. So what do we mean by normal data, right? Everyone must have heard about a histogram. So what does histogram show? It shows us that, number one, that there is a middle value or an average value or a median, right? And then the spread of the histogram shows us how dispersed the data is, right? So on the histogram, you should be able to see that, that the data is distributed normally, right? Or it shows a bell, it has a bell-shaped curve. And by that bell-shaped curve, what we mean is that our data, the spread of our data, is similar to the spread of data that you would see in a population, right? So essentially what inferential statistics is doing is it tries to show you that the relationships or inferences that you're drawing from your study sample correspond to those that exist in the population as well, the larger population from which that study sample was drawn. So for the upper row, when we talk about Pearson correlation, what it is essentially saying is that there would be two continuous variables, right? Like we talked about, BMI correlates with, let's say, systolic blood pressure. Both are continuous variables, but we need to see that they have a normal distribution, right? If they do not meet the assumption for normality, you can run a Spearman correlation as well. The Spearman correlation is mostly run for variables with ordered categories, but it can also be run for non-normal data, because Spearman correlation does not assume that the data is normal, right? What it does is it does not use the actual values of the data, rather it assigns rank to the data. So the minimum value will have a rank of 1, followed by 2, 3, 4, 5, and then those are correlated. The ranks are correlated, right? So that is why it is a very good alternative for Pearson correlation. Now, let's move on to the one sample t-test versus signed rank test. Now, what are we doing here? So in SPSS, what we are doing is that we have a continuous variable. Let's say in our study sample, that we ran a study on 200 study participants, and we calculated data on their BMI, body mass index. And the average value of BMI in your study sample came out to be 32, right? That's quite high. And we want to see that if this mean value of BMI in our study sample, does it reflect the value that's of the whole population, right? So for instance, in a study, you find that which has a sample size of 100,000 in the same population, you find that the average value of BMI in their study sample of 100,000 people came out to be, let's say, 22. And in your study sample, it came out to be 27, which is just based on 200 participants. You can compare them using one sample t-test and see if they differ significantly or not. So in my understanding, if you compare 22 with 27, it is going to differ, right? So in your smaller survey or smaller study, the BMI, the average BMI that you saw does not really correspond with the population mean, and there's got to be a lot of error in it, right? And that error could emerge from multiple sources. Number one, maybe it's because you had not really selected your study participants randomly, right? Or so there could be a lot of these things. Doctor, yeah. And so if you and you can use this one sample t-test when you have a normal distribution, and if you don't have a normal distribution, you could compare your continuous variable with population mean for non-normal data using signed rank test, right? And independent t-test for independent samples, what it does is it shows you group differences between group differences for a particular variable. So for instance, it says dichotomous variable. So that would be something like gender, male, female, right? And you're trying to compare BMI between male and females, for example. So you have a dichotomous variable and you want to see if the gender is associated with BMI. So your hypothesis would really be if males have higher BMI than females, or if males have lower BMI than females. Those are essentially your hypothesis, right? And that could be tested using independent t-test. But for this particular test, you need to make sure that your continuous variable, i.e. the BMI, has a normal spread for both separately for male and female, right? If it is normal, you run an independent sample t-test. If it's non-normal, you choose man-Whitney U-test. And why do we choose man-Whitney U-test? Because it allows us, number one, you have a couple of choices there. Either you can use median, or you could use distribution distribution that does not really require uh, any normal distribution, right? And then when we talk about paired t-test and Wilcoxon test, now paired t-test means that there is a one dichotomous and one continuous variable, right? But the dichotomous has to be in pairs. So for instance, you run an experiment, right? And it's a randomized controlled trial, not controlled, it's a randomized trial, for example, or it is a pre-post study that has, let's say, you test an antihypertensive medication, right? You give that antihypertensive medication to 100 people. You note their blood pressure before the treatment and then you note their blood pressure after the treatment, right? And you want to see if the antihypertensive has improved the blood pressure after treatment. So what you're going to do is you're going to compare blood pressure before treatment with blood pressure after treatment, right? And see if there is a statistically significant difference between the two values. And that would be done by pair t-test if the data for hypertension or the data for blood pressure is normal. If it is non-normal, you just use Wilcoxon signed rank test. And Wilcoxon signed rank test again does not really use the values for data that we have. It ranks them first and then runs a test on them. So that's a basic concept. And if you have so ANOVA test is analysis of variance test, right? So in this one, it is something similar to independent sample t-test, where you have two categories, right? In this one, you will have more than two categories. And they, for example, let's talk about gender. So male, female, and the third one was prefer not to say, or male, female, and non-binary, right? Now you have three categories here, and you can compare the blood pressure or BMI between these three categories using the analysis of variance test. Now, an important thing about this is that in ANOVA test, you're not really analyzing the mean value, if they differ or not. You're looking at variance, the spread of the data. If your data is normal, you run ANOVA test, one-way ANOVA. And if it's non-normal, you run Kruskal-Wallis test, which is the non-parametric alternative to the analysis of variance test. So do we have any questions regarding this? I'm just going to open up the chat box.
So I have some questions. So simply that means is when you're running correlation analysis between two non-continuous variables, you always do the bottom one, like Spearman, sig rank, Mann-Whitney, and all of the tests in the bottom. Is that correct?
Yes, only if the histogram that you see for the continuous variable does not come out to be normal.
Mm-hmm.
Right? If it is skewed to the left or right, or it may be kurtotic, right? So it all depends on your histogram.
Okay, I think I have another question, but Ms. Sheikh asked a question. Can you explain the pair t-test again?
Check. So paired t-test. Now again, the paired t-test would mean that it is going to be a dichotomous variable. Sorry. So it is going to be a dichotomous variable, right? But the only thing is that instead of having a dichotomous variable based on gender, let's say male and female, they are not related to each other. But when you say before treatment and after treatment, that pair is correlated, right? That the value of after treatment would depend on the value before treatment as well, right? So these variables, the values before and after treatment, are sort of correlated. So that is why you do not run an independent sample t-test, but a paired t-test, because that takes care of that correlation between the pair or between the dichotomous categories that you have in that particular variable. Does that make sense?
Is there any other situation besides before and after where will you use the pair t-test?
So for instance, if you run a survey, right, after a workshop, you check competency of participants before the workshop and after the workshop, right? Before, respondents who have really high competency before the workshop, chances are that after the workshop, they're still going to have a very high competency, right? And those who have weak knowledge or competency before the workshop, chances are that their knowledge would increase, but not as much as those who were high achievers or had high competency before the workshop, right? So these two values before and after the survey or after the workshop are correlated, right? So this is a situation where you would use a paired t-test.
Okay. So, in this, for example, for analysis of variance for non-dichotomous, so let's say if you have a categorical variable or an ordinal variable,
Yeah.
you are doing correlation analysis with the continuous variable. So that's when you will use ANOVA if your distribution is normal.
Yes. Yeah.
Okay. One last question, and I think then we can move on or whatever is on your plan. When you are assuming for normality, is it based on the independent variable or dependent variable?
So normality is always for the continuous variable, right? So when you talk about dichotomous variable or trichotomous or multiple categories, you cannot really check their normality, right? Normality is always for continuous variables. So for Pearson or Spearman correlation, both the variables are continuous. So you have to check normality for both of them. In independent sample t-test, right, you have to check category, you have to check distribution for the dependent variable, whatever it may be, for both the male and female. So you'll have to stratify or create a separate histogram for males and a separate histogram for females, and then see if both are normally distributed. I'll just share my screen again. Yeah. So we covered quite a few concepts, right? So this is just an introductory level introduction to these concepts. And you could have a 1 hour lecture on each of these concepts. So I know that with no background in biostatistics or medical statistics, it is going to be a difficult thing to grasp. So you may have to read up a bit more. So when we talk about regression analysis, let's start with a case study on linear regression, right? So in this particular case study, a group of researchers are trying to predict lung function in smokers, right? So what they are trying to do is that they are trying to examine the health effects of smoking, where researchers gather data on the age, number of cigarettes smoked per day, year of smoking from a group of long-term smokers. And then they also measured lung function tests, such as the forced expiratory volume in 1 second, FEV1, right? Now, what they are trying to do is they are trying to predict lung function here using a couple of biological variables or a couple of biological characteristics of long-term smokers. And for this particular data, where they have values on a number of variables, including age, number of cigarettes smoked per day, and years of smoking, and FEV1, they used multiple linear regression, where FEV1 was a dependent variable, and age, number of cigarettes, and years of smoking was an independent variable, were independent variables, right? They found that the three predictors, right, age, number of cigarettes, and years of smoking were significant and negatively associated with FEV1, with years of smoking having the largest effect size, right? And they concluded that this model could be used to predict lung function decline in smokers based on their smoking history and age, right? So what they are trying to say is, number one, that FEV1 can be predicted using age, number of cigarettes, and year of smoking. So these sort of variables form a group of smokers, right? They found that these predictors were significant and negatively associated with FEV1. So with lung function, increasing age was inversely related. Number of cigarettes smoked was inversely related, and years of smoking was inversely related as well. So the higher the age, poorer the FEV1, the higher the number, more the number of cigarettes smoked over the years, the poorer the FEV1, and more the years of smoking, the poorer the FEV1 value would be. And then they say that the years of smoking had the largest effect size. So the most important or strongly correlated, so years of smoking affected FEV1 value or lung function more than age and number of cigarettes, right? And they said that we can predict lung function decline in smokers using these three variables. So in practice, in medical practice, when you are taking history from a patient, and that patient is a smoker, and you see that he is 60 years old, smokes 50 cigarettes per day, and has been smoking for the past 30 years or 20 years, right? You can conclude that, or you would be able to deduce that, from, I read that in that particular study, these three variables are really important, right? So what is regression? So regression is a very fundamental statistical tool that helps us understand the relationship between dependent and independent variables. So in essence, it allows us to predict the outcome of one variable based on the value of another variable, right? Or another set of variables. So in medical context, a researcher might use regression to predict the outcome of a treatment based on various factors such as age, gender, or genetic factors. So for instance, if you conduct a study on 200 patients, right, your outcome variable that you're interested in is hypertension or blood pressure before and after treatment with an antihypertensive. And you want to know if this treatment effect differs with age, gender, or genetic factors, you could just run a multivariable regression analysis. So these are the sort of questions that this particular technique allows us to explore. So it has countless applications and countless extensions that we'll talk about later on. So what is the basic concept of linear regression? So this is a fictitious study, an example that I took from a book on medical statistics, where they tried to correlate or check or look at the relationship between body weight and plasma volume, right, in liters, and body weight in kg. And they developed or plotted a scatter plot, right? And these are individual data points, right? And then what they were interested in seeing was that number one, if there is a correlation or relationship between the two variables. Number two, was it positive or negative? And number three, is it strong correlation or weak correlation, or does the correlation not exist at all, right? So what they did was they plotted a line of fit here, a regression line here, right? And this best fitting line is plotted using the method of least squares, right? If you don't use this method, then different analysis statisticians will, subjectively draw this line, and it could be up or below. So we have a standard method for it, right? And what they were able to do was that for the value of 70 in body weight, if a person has a body weight of 70, right, this is going to be their plasma volume. So this is a simple scatter plot with a regression line. But the method used here for fitting this line is method of least squares. Now, what does this method of least square does is that it draws a regression line between these data points so that this line is close to all the points, all the data points, right? It tries to minimize the distance between the data points, right, and itself, the regression line itself. In statistical terms, it tries to minimize the sum of squared errors, right? So when you see here that although it tries to be as close to each data point as possible, there is still some error here. So this line is particularly close to this data point. So the error, the residual error is particularly low, but for this data point is quite large, right? And then you hear about, so all of this could be represented by a simple statistical notation. Y equals beta naught plus beta 1x plus residual error or epsilon here, right? Y is the value for the plasma volume. Beta naught, it is related to intercept. So intercept meaning the value of the outcome variable when the predictor variable is 0. And beta 1 corresponds to the slope of the line. So in this particular example, it relates to increase in plasma volume corresponding to a unit increase in body weight, right? X is the value of the value of body weight in kg here, and E or epsilon is the residual error, which represents the variance or the relationship that is not explained by the model. There's always going to be error in a regression line, right? So what you're trying to predict here is quite a few things that we have gone through. So this is a very simple demonstration of what a linear regression does. So do we have any questions so far? I'm just going to open up the chat box. Oh, no questions so far. So it is quite similar to what you're talking about, Rija. Yeah. So the general concept is linear regression predicts a dependent variable based on the independent variable when the relationship is linear, right? Just like in the Pearson correlation and the correlation analysis that we had talked about. So let's begin with another case study. So researchers might use linear regression to predict life expectancy based on an individual's BMI. Is the BMI of an individual related to life expectancy, right? So it gives us an equation that represents the line of best fit through the data, what we talked about previously. And the statistical or mathematical notation for linear regression, y equals beta naught, outcome value equals intercept value plus beta 1 slope, x value of the BMI variable plus error. This can just be translated to life expectancy equals life expectancy when BMI is 0 plus slope of the line into value of BMI plus error. So this is a very simple bivariable regression model with only two variables, life expectancy and BMI, where you are trying to predict the value of life expectancy based on the BMI of a particular individual. So there are quite a few types of regressions, right? But today we are just focusing on linear regression, which only looks at or which only produces tangible results when the relationship between two variables is linear, right? And the outcome variable would be continuous. There are quite a few extensions for these particular for regression, including non-linear regression that looks at non-linear relationships, logistic regression that looks at where the outcome may be binary, Poisson regression where the outcome variable is count or ordinal or ordered, and survival analysis where the outcome variable is time to event, right? Time to death, time to to stroke episode, right? And these come under the category of generalized linear regression models. And once you have a thorough understanding of linear regression, extending those concepts to these generalized linear regression models is not tough. So we often come across terms such as multiple regression or multivariable analysis, right? So what does it really mean? So multiple regression is used when there are multiple independent variables. So previously, we just modeled in a regression model 2 variables, right? But in multiple regression, we have multiple independent variables. And then the equation for linear regression can be extended, right? Where we try to describe how each independent variable influences the dependent variable. So for instance, multiple regression can be used to examine how age, diet, and physical activity together influence the risk of heart disease. So we're just extending the bivariable regression equation or notation to include multiple predictors or independent variables, right? So how do you calculate slope of line? I'll come on to it later on because we have a slide on it. So before moving on to regression itself, we really need to understand the concept of confounding variables, right? And crude and adjusted effect sizes. Now, what does confounding variable mean? We have covered this concept in our previous slide, but let's just go through the definition again. So confounding variable is an external variable that affects both the dependent and independent variables, causing a spurious association. If not controlled, this is an important concept here. Confounding can lead to incorrect conclusions about the relationship between the independent and dependent variables. But, you know, this was a major limitation when we were conducting correlational analysis, right? But the good thing about regression analysis is that we can control for confounding variables by including them as an additional independent variable in the model. So this would give us a clearer picture of the true relationship between our primary independent and dependent variables. Now, what are crude and adjusted effect sizes? Now, you often look at these terms when you read epidemiological papers. That adjusted effect size allows us to isolate the impact of a particular variable while holding other variables constant, right? They help us understand the contribution of each independent variable to the dependent variable. So for instance, let's say you're trying to look at the relationship between gender and BMI. So you run a study with 500 participants, right? You collect their data on gender, if they're male or female, and you try to predict their BMI based on gender, right? And your regression model shows that that gender is significantly statistically associated with BMI of the participants, right? And females have a lower BMI than males, right? But in previous papers, you read that age is an important variable or is an important factor or correlate for BMI. Those who are older have a higher BMI, and those who are younger have a lower BMI. So you may think that maybe it's not really the difference between the genders, right? It is really the age that's driving it. So for example, if the females included in your studies had a lower age as compared to males, that would mean that because they have a lower age, they have that's the reason they have lower BMIs as well. And because males in our study sample tend to be older, That's the reason they have higher BMIs, right? So you can adjust for this confounding factor in multivariable regression. So instead of having only gender as a predictor variable, you also add an age. So what that would do is that would give us the regression coefficients for male and female while holding age constant, right? So it tries to remove the contribution of age, right, on the relationship between gender and BMI. I hope that makes sense. It is just like the confounding concept of confounding that we had studied or explored previously. And before moving on to formal regression analysis, right, we need to think about a few assumptions. That before regression, there are quite a few assumptions that data needs to fulfill if we want uh, let's say true results or good results, right? So these assumptions include linearity, that the relationship is linear between two variables, independence, that the variable are not correlated, homoscedasticity, that the spread of the data, right, is homogeneous, right? It does not really show a pattern, and normality, that the data distribution is normal. And all of these would be assessed before running or interpreting a regression analysis. So that is why it's really important to go through these critical concepts, because violation of these assumptions can lead to biased or inefficient estimates. And regression also has a few caveats. It can be influenced by outliers, and it assumes that relationships are linear, which may not always be the case. And lastly, it does not prove causation. Unless you're running a longitudinal cohort study, we cannot really prove causation, right? So do we have any questions so far? No questions so far. Let's move on. So we'll talk about the assumptions now, because this is a very important.
There is some background noise that is coming.
Sorry?
There is some background noise that is coming.
So regarding the assumptions, so there are quite a few assumptions, because that your data needs to fulfill if you're to receive good results from regression or true results from regression analysis. Firstly, you need to see that the data is normal, distribution of the data is normal. And that could be explored using PP plots and histograms. You need to show that the association between the dependent and each independent variable is linear. That can be shown using scatter plots. There is no autocorrelation, right? And we'll go through these in detail later on. That can be explored using Durbin-Watson diagnostic. That there is no multicollinearity. That can be assessed using the values of tolerance and variance inflation factor. That there is no homoscedasticity, and that could be done just by running a scatter plot of studentized residuals versus predicted values. And then that there are no outliers or influential cases, right? And these need to be explored before running a regression analysis. So what does multicollinearity mean? It just means that two or more independent variables in a regression model are highly correlated. So for instance, you develop a multivariable regression model, right? And you add in variables that are strongly correlated with each other. So for instance, let's say age and number of years since graduation, right? So higher the age, older the person, older the date of the graduation would be, those are correlated. So we need to see if they are highly correlated or not. Because if they are highly correlated, it would just it would not fulfill the assumptions for your regression analysis. And these are explored using the values of various inflation factor, which measures the inflation and the variances of a parameter estimates due to multicollinearity. And the rule of the thumb is that a VIF value larger than 5 indicates higher multicollinearity. So it's a common output that SPSS produces for a regression model, right? Just to look at if multicollinearity assumption is being fulfilled or not. And then there should be independence. There is assumption of independence, right? So what it means is that outcomes from each observation in the data are not related to each other. So outcome of one observation does not give you any information about the outcome of another observation. And this could be detected using by plotting the residuals in the order that they were observed. So for instance, consider a study in a hospital investigating the impact of different surgical techniques on the rate of post-surgical complications. So over the course of several months, surgeons perform hundreds of surgeries using various techniques, and data are collected on whether or not patients experienced complications within 30 days post-surgery. The independence assumption here would suggest that the outcome of one surgery is not related to the outcome of any other surgery. But imagine, over the course of this study, the surgeons are becoming more experienced and improving their skills. Because of this, the likelihood of surgical complications could be decreasing over time. And this could violate the independence assumption that the outcome of surgical complication are not independent of each other because they are related by the time of surgery, right? So the rate of surgical complication falls as the study progresses. So the values for outcome, penultimate values or subsequent values correlate with the previous value. And if this is the case, regression analysis should not be conducted. We should go for time-dependent data analysis techniques such as time series analysis or survival analysis, right? Or techniques or extensions of regression that account for repeated measures. And then, so independence assumption can be explored using a very simple technique of Durbin-Watson stats, denoted as T. And this stat, it detects the presence of autocorrelation. So the Durbin-Watson stats ranges from 0 to 4. If T is equal to 2, it suggests no correlation, right? Between 0 and 1 or greater than 3, negative correlation. Less than 1 and greater than 3, positive correlation. And then an important thing about outliers and influential points. So whenever you're doing regression analysis, you need to visualize your data using box plots and see if there are data points or participants that scored very highly or very poorly when you compare it with the mean of the study sample, right? So imagine you're a sports coach, right? And you want to understand how athletes that are training under you, how does their height correlate with their sports performance? So you gather data from 30 athletes are training under you, plot each athlete's height on the x-axis and their performance on the y-axis. And then use a regression analysis to draw the best fit line through your data points. Now, suppose one of the athletes who is significantly taller than their peers, right? They also happen to have the best sports performance. So this athlete's data point will be far away from the others. It would be far away from the mean value, meaning that it is an outlier or a special case. And it can have a big impact on the regression line. So what it will do is it will try to deviate the regression line or track the regression line towards itself. And what would happen is that in the end, the sports coach may just look at the data, the regression line, and say, it just means that those athletes who are significantly taller also perform better, right? Because the line just tilted towards the athlete who was significantly taller and also had the best performance. And he may end up not recruiting shorter students in later on, right? Because he thinks that those who are tall also have better performance. And all of this, outliers, influential points in your data set can be identified using case-wise diagnostics, leverage values, and Cook's distance, right? Case-wise diagnostic, plus minus C is the usual cutoff, where a residual may be considered an outlier. Then there are leverage values and Cook's distance. So we're not going to go in a lot of detail, but SPSS generates all of these points, and the cutoff points, you can just get them from this PowerPoint presentation. So we're not going, because the time is really short, we're not going to go in a lot of detail. Then there is a homoscedasticity assumption, right? So this is an important assumption for running regression analysis. Suppose you're a researcher studying the effect of a new drug on lowering blood pressure, and you conduct a clinical trial with a diverse group of participants who vary in range from 20 to 80 years old. Your dependent variable is reduction in blood pressure after taking the drug for 4 weeks, and the independent variable is the age of the participants. Now, for running regression analysis, you have to make sure that your data fulfills this assumption. You need to make sure that the variability in blood pressure reduction is consistent across all age groups. In other words, if the blood pressure changes in young participants should have the same amount of variability as the blood pressure in older participants. If this is not the case, so if the blood pressure changes in young participants are really narrow, for instance, their variability is really narrow, like that after hypertensive treatment, their systolic blood pressure is between 120 and 130. But for older participants, this variability, or the range is between 120 and 180, then there is heteroscedasticity, right? Variance is not homogeneous across the data set, across the age groups. In this case, you would get misleading results from regression analysis. So homoscedastic just means spread or dispersion of the outcome is the same across all levels of an independent variable, right? And this could be checked by creating a plot where you compare the residuals against the predicted values. If the points are randomly and evenly spread around the horizontal axis, then data is likely to be homoscedastic. And if there's a pattern, the data might be heteroscedastic. So this is like saying that spread of arrows around the bullseye changes with different targets, right? You need to make sure that for instance, imagine that you're shooting arrows at several targets, right? So homoscedasticity is like saying that your spread of arrows around the bullseye is the same, no matter which target you're aiming at, right? And if this isn't the case, then you have a situation of heteroscedasticity. And this is a problem because it makes our predictions less reliable and our regression results to be less valid. So this is the plot where we correlate standardized residuals with predicted values, right? Now, these three plots, scatter plots, they correspond to situations where we do not meet assumption from homoscedasticity. So for instance, if it is funnel shaped, the spread of the data here, the variance is low, but the variance here is really high. The spread of the data points is really high. Opposite case here, on the left side, spread of the values is narrow. But on the extreme right, the variance is really high. Spread of the data is really high. And same for this fan-shaped scatter plot, right? In the middle, spread of the data is narrow, but on the extreme sides, the left and right, the spread of the data is, data is really spread out. So if this is the case, you will not have valid results. Then concept of confounding, I'll just skip this because we have talked about it in a lot of detail. Do we have any questions so far? So I know this is quite a dry subject, but I have tried to keep mathematical notations and statistical derivations to a minimum here. And we're just talking about general concepts and looking at figures. So we talked about, so one of the questions was previously that how do we know that confounders exist and how do we control for them, right? There are quite a few techniques here. For instance, you may have read about randomization in randomized control trials. So at the baseline, you randomize the participants, right? So what that random assignment of participants, placebo and treatment group does is that it can control for both known and unknown confounders. Then there's a concept of matching or a technique of matching, where what you do is, this is usually performed in observational studies, where each participant in one group is paired with a similar participant in the other group, right? And this can control for known confounders, but not unknown ones. So for instance, for each participant aged 39 years old, male, resident of city A, right? You match a similar participant, aged 39, male, resident of city A, in the control group and the treatment group respectively, right? So this is a matching technique. But the only downside is that you are controlling for known confounders, age, gender, residence, or city, right? But there may be unknown confounders as well that you do not know about, and that you had not considered while matching the participants. Then there's a concept of stratification, where the data is divided into strata based on the levels of the confounder, and the effect is estimated within each stratum. So for instance, you may see that the thing we talked about, let's say response to hypertensive medication, right? That's your outcome variable. And you see that the effect differs between males and females, right? And then, but you may think that the difference in males and females is driven by young age and old age. If you stratify the data and produce results for males and females who are young, and separate results for males and females who are old, right? And then you can try to stratify or try to take out the effect of confounding factor, right? Which in our case was age. But then you can also use statistical adjustment in regression analysis. If you just add in that confounder of age in a regression analysis, you would have controlled for its confounding effects, right? Because what you're trying to do is you're trying to, when you add in age and gender, both the variables in regression analysis, and look at its effects on the hypertension or blood pressure, right? What you are doing is you're trying to look at the association between the gender and blood pressure while keeping the age constant. And this is what you call statistical adjustment in regression analysis, right? Then there are propensity score methods which are advanced statistical methods to control for confounding in large observation studies. So quite a few concepts here. We talked about crude versus adjusted effect sizes, right? But just to recap, that adjusted effect sizes in regression analysis are used to quantify the strength of the relationship between the predictor and the outcome, taking into effect the influence of other predictors or the confounding variable, right? So if you just look at the association between gender and hypertension and blood pressure, that would be a crude effect size. But if you control for age in it, right, if you enter age in that particular regression model, then you will get adjusted effect sizes, because the association or the relationship between gender and hypertension or blood pressure has been adjusted with age. We talked about limitations. So regression analysis can have a lot of limitations. Influence of outliers, we have talked about it. Linearity assumption, that there should be a linear relationship between independent and dependent variables. It should either be increasing or decreasing, right? You cannot have a curve increasing, plateau, and then decreasing. That's a non-linear relationship. Regression doesn't prove causation, and then overfitting and underfitting. Your model could be too complex or too simple, right? We're not going to go into a lot of detail about overfitting, underfitting, and all of these because these are advanced concepts. So let's just demonstrate regression analysis on SPSS. I'm going to stop sharing my screen and wait for questions before we move on to demonstration in SPSS. Demonstration is really easy. Getting concepts right, that's really important. So do we have any questions so far? No questions. Would you like to have a 10-minute break before we move on to demonstration?
So how long it's going to take with demonstration?
Let's say about 15 minutes, not more than 15 minutes.
So let's ask people if they want to finish and get done in 15 minutes, or they want to take a break for 10 minutes and come back.
Let's just take a 10-minute break. Yeah. Oh, we can finish. Okay. So let's start with demonstration. I'm going to open up my SPSS file. We're utilizing a fictitious data set. Yes. So can everybody see the screen?
Yes.
So if you have, so let me just share, if you have a command on regression analysis, that's the most advanced you can get at this stage. And all of the international publications that I had during my early years of research, all of them were able to get published in international journals just because I used regression and not bivariable statistics such as independent sample t-test or simple correlations. So to get into a higher impact vector or a more reputable journal, you need to be using these regression analysis because they provide you with more valid results, control for confounding, and a lot of other issues that exist with just bivariable techniques. So just master regression analysis, but you only master it when you have mastered the more simpler statistical tests. So coming on to my screen on SPSS. So this is a fictitious data set that I took from a website called Lead Statistics. I'll give the link to that website, which is an amazing website for learning SPSS and to understand statistical techniques as well. And it also has a very low subscription charges. And I used that website in my initial years of research. Quite a useful resource. So what we have in this data set is the first variable is case number. So it's just a study ID for participants. Age of participants, weight of participants, heart rate of participants, gender of participants, and then VO2 max, right? Just give me a moment, please. I'll be back in just 5 minutes. Sorry. So yeah, let's take a 5-minute break. That's fine. So let's begin with the demonstration. So in this data set, we have quite a few variables here. Firstly, case number ID of the study participants, right? It is classed as a nominal measure or a categorical measure, right? And then we have age of participants. It's a scale, it's a continuous variable. So it has been mentioned here as scale. We have heart weight of the participants, heart rate of the participants, and gender of the participants, right? Gender is classed as nominal here because it has two categories, male and female in the data set, right? And lastly, the variable is VO2 max, which is a variable related to cardiorespiratory fitness, right? So what we are trying to do is, in this particular data set, we have a data of about 100 participants, right? And what we are trying to do is, we are trying to predict VO2 max or cardiorespiratory fitness of these 100 participants using the gender, heart rate, weight, and age. So really what we are trying to see is, if by using all these variables, can we predict the value of VO2 max? If the gender of the participant is female, heart rate is 72, weight is 50 kg, and age is 20. Can we use these values to predict VO2 max? So just think about the regression equation here. The regression equation would be VO2 max equals intercept plus gender into beta coefficient, right? Heart rate value into its beta coefficient, value of weight into beta coefficient, plus age of the participant into beta coefficient plus error, right? You add all those values and you would get the value of VO2 max. Now let's move on to demonstration. Now to run linear regression, just move on to regression. Click on linear, right? So just a disclaimer here that we are not going to run exploratory data analysis, right? Before running linear regression, we need to look at a lot of things like distribution of these variables. We need to look at if the relationship between the dependent and independent variables is linear, right? If there are any outliers, we need to run exploratory data analysis here, a couple of visualizations, scatter plots, histograms, to look at those assumptions are being fulfilled or not. But SPSS, the good thing about SPSS is that it does allow us quite a bit of flexibility here, because it can test most of these assumptions in this linear regression module. So move on to the linear regression module here, right? We add in VO2 max. Let's just reset here. VO2 max is our dependent variable. This is what we are trying to predict, right? And we are trying to predict it using variables of age, weight, heart rate, and gender. These are predictor variables here, right? The method for this should be enter. It does have a few more methods as well, stepwise, remove, backward, forward, but these are how to scope for this course. We can have a more detailed discussion on them because they need dedicated time. Click on statistics. We're interested in getting estimates for beta coefficients and unstandardized betas, right? Because they would be inputted in the regression equation. We would be interested in confidence intervals, right? We want to see if the model is fit, right? Descriptives. We are interested in getting part and partial correlations, collinearity diagnostics to look at multicollinearity, Durbin-Watson test to look for autocorrelation, case-wise diagnostics to look at influential cases or outliers, right? We need all this information to see if the assumptions are being fulfilled. The This is what we spent our last 1.5 hours on. Click on plots, right? Now, these plots are going to produce histograms. Click on histograms, normal probability plot, because we want to see if the residuals are normally distributed, right? Normality assumption. And normal probability plot is also going to tell us about the normality. And then we want Z residuals from here in the y-axis and Z spread value in the x-axis. So what we are trying to do is we are trying to produce a scatter plot where on x-axis we have the predicted values and on the y-axis we have the residuals. And this is going to produce a scatter plot where we will be able to test the assumption for homoscedasticity. The partial plots, where each partial plot would show us a scatter plot between each independent variable and the dependent variable, right, the continuous ones. And it is going to plot the relationship between them. And since it is a partial plot, it is trying to adjust for confounders or other variables as well. Click on save. What we want here are the predicted values, unstandardized, studentized, and studentized deleted. We want distances values, Cook's values, and Lagrange values. These are for looking at outliers or influential cases that could influence the results of the regression model that we create, right? Go to options. If you have a lot of some missing values, not a lot, less than 5%, for instance, in the outcome variable, you can just replace them with mean, right? The missing values can be replaced with mean, but since we don't have any missing values in our data set, we don't need to use it. We'll just say exclude cases list-wise. It's irrelevant here, really. So this is all we need to run a regression analysis result. Do we have a
question?
Yeah.
So on the previous one, I think it was under saved. Why did we not pick for adjusted and only pick for unstandardized? Like when you're talking about crude versus adjusted.
No, this does not relate to the adjusted and crude effect sizes. This is just for residuals. To plot the residuals against predicted values to look at the assumption for homoscedasticity. So the adjusted effect sizes, I'll come to that later on, right? So I'm going to press OK now. So we get the output section. Can you see the output of results?
No.
Let me reshare my screen. Yeah, can you see it now?
Yes.
So what do we see in the results for regression? Number one, descriptive statistics, right? It gives you mean, standard deviation, and sample size for the dependent and independent variables, right? Then you can look at correlations. So these are just Pearson correlations that we had talked about. These are the value of R coefficient. These are the associated p-values, and these are the study sample, number of study participants, 100 for each variable, right? If they were missing any missing values, it would have reduced. So you would see here that in Pearson correlation, that the value of VO2 max correlates perfectly with VO2 max because these are essentially the same values. VO2 max correlates negatively with age, correlates negatively with weight. Older the age, poorer the VO2 max, so cardiorespiratory fitness. Higher the weight, poorer the VO2 max. And then it has a very weak association with heart rate, right? And a positive association with gender. And if you go to this row, this just shows the p-values, right? So the correlation between age and VO2 max is statistically significant because the p-value here is less than 0.05. Same for weight, statistically significant, but heart rate, the relationship between the VO2 max and heart rate is not statistically significant because the p-value is significantly higher than 0.05, right? And then the association between gender and VO2 max is also statistically significant. Since gender is a dichotomous variable here and VO2 max is a continuous variable, you might be thinking about how are we using this to do this correlation. So this is a special case and it's called point biserial correlation. We can talk about that later on in the discussion if you want. And then let's move on to this table. It is telling us the dependent variable is VO2 max. These are the variables entered as predictors, right? And the method is enter, that we entered all these variables in the regression model, right? If we had used forward, backward, stepwise methods, it would have shown them here. And that is those methods are not demonstrated here. Now look at the model summary, right? What does it tell us? Quite a few values here. Let's look at the Durbin-Watson diagnostic, Durbin-Watson test for autocorrelation. We had said that it should be equal to 2, almost equal, approximately equal to 2, to show that that our outcome is not autocorrelated, right? So it is approximately equal to 2. So we can say that our data fulfills assumption of autocorrelation. You look at R squared. What is this R squared telling us? It's telling us that gender, age, heart rate, and weight, all of these predictors explain 57.7% variance in VO2 max, right? So about 58% of variance in VO2 max can be explained by gender, age, heart rate, and weight. And rest of about 42% of variance would be explained by other predictors that are not currently in this data set, right? What is this adjusted R square value telling us? So adjusted R square values, this is just telling us that that this R square, that gender, age, heart, and weight can explain 55.9% of variance in VO2 max, right? So why is there a difference between adjusted R square and R square? Because in this one, R square has been adjusted for number of variables entered in the regression model. This relates to the concept of overfitting and underfitting. If you have too many variables in your regression model, it's good to use adjusted R square as a value for explaining proportion of variance explained, because it penalizes the regression model for number of variables entered in it. Let's move on to the ANOVA table, right? It talks about residuals, sum of squares. It's really trying to tell us if in the regression model, the line of fit that had been, the regression line that had been fitted, right? What is the extent of error in that, right? Residual. And the line of fit tried to minimize the sum of squares, right? Sum of the squares of errors. But the most important values here are the F value and the P value, right? We'll talk about this later on. Let's move on to the coefficients. Now, this is the table that's usually, or that's really reported in your research papers. You have the value of constant, which is the intercept, and then you have your predictors. And in the end, you have collinearity statistics, the value of variance inflation factor and tolerance that tell you if multicollinearity exists in your model, right? And then there are some important values here related to Cook's distance and Lagrange value. Why did we ask for these values? To look for influential cases. And we had talked about their but in our data set, the maximum value is 0.14 for Cook's distance and 0.162 for Lagrange values, right? So these are not really significant. So our data does not really have any significant outliers. This histogram shows us that there is normal distribution, approximately normal distribution. You can look at this beautiful bell curve here, right? So the residuals are normally distributed, and it fulfills the assumption for multiple regression. Then we look at scatter plots. The scatter plots, what does it do? Dependent variable is VO2 max, right? And it is trying to plot regression standardized predicted value with regression standardized residual values, right? So these need to be linearly distributed, right? It is quite linearly distributed. So we fulfill the assumption for linearity when all the predictive variables are considered together. And then we look at partial regression plots. Let me just use this. I'm going to just edit this one. Let me just, and then can you still see my outcome screen?
Yes.
Yes, okay. And then let's move on to the partial regression plot. Now this is going to plot, so this was previous plot, scatter plot was for all the predictor values taken together, right? And then we have partial regression plots for individual predictors. Now this needs to correlate linearly as well. And it correlates age with VO2 max. And it's a partial regression plot. So that means it is adjusted for other variables. Whatever other variables and confounders you have, such as heart rate, gender, and all that, right? And then other partial regression plot between weight and VO2 max, right? It is also linear, negative, inverse, right? That with increasing weight, right? So it is inverse. Weight increases, VO2 max decreases. So this is also quite linear, and it is fulfilling our assumption related to linearity. So we don't really look at, and then with the heart rate, again, it is quite linear, increasing, decreasing, or no relationship at all. We don't really look at partial regression plots for categorical or dichotomous variables, right? So no need to look at this one. So we have fulfilled most of the assumptions, or all of the assumptions for the regression plot. Now I'll take you to my PowerPoint presentation where I have copy pasted all the above tables, and I try to annotate them for the participants, right? And we can discuss those in more detail. So I'm going to take you to my, yes. So can all of you see my screen?
Yes.
So this was one of the most important tables that we talked about, right? R square, adjusted R square, and standard error of the estimate. What it is trying to tell us that variability in Y or variability in VO2 max is explained by gender, age, and weight, And this is the extent to which they explain the variance in it, right? All of them together. So about adjusted R square is 50.2%. So about 50% of the variance is being explained by these variables, and rest of the 50% is explained by other variables that we did not really measure, right? Then we look at the table for statistical significance. Just look at the F value and the P value here. These are the most important values. So the F value tests the null hypothesis that all of the betas equal 0, the coefficients, beta coefficients for all predictors, right? And the significance corresponds to the P value. It's less than 0.001. So it means that our regression model is fit, is good enough. And we can reject the null hypothesis and conclude we have enough evidence to believe that the predictors, covariates, or variables of gender, age, and weight have predictive power in our linear model. And they are significant, and they can predict variability in VO2 max in a valid way, right? And then the next table, this is a shortened version of the table with the beta coefficients, right? So the constant here, 68.725, is the intercept, right? So if you develop the regression equation, constant plus age plus weight and gender multiplied by their betas plus error, right? 68.725 would be the intercept value of
Slope.
no, it would be the value of the outcome variable when age, weight, and gender are taken as 0. And the value of B here, this is unstandardized B, right? Unstandardized B coefficient. And it gives you the value for the slope, negative 0.153, negative 0.353, and 12.29. So number one, that what is the slope telling us? That for each unit increase in age, the outcome of VO2 max would decrease by 0.15 units. So with minus sign, you know that it is decreasing, and 0.15 means that the decreases by 0.15 units. With weight, if you increase the weight by 1 unit, the decrease in VO2 max, because there's negative sign, would decrease by 0.35 units, right? And if you if you compare females with males, right, we need to check how it was coded, but the difference between females and males is of about 12.29 units. So this would be the increase in VO2 max if you move from female to male. I will just have to confirm that association because we need to see if female was coded as 0 or 1. And then the standard error shows us that this is the error in these B coefficients, right? Because these coefficients came from our study sample. And if you compare that to the population, then this is the error that we could expect. Now, beta is standardized coefficient. It is approximately equal to correlation coefficient, right? And it is, in essence, number one, approximately equal to correlation coefficient. And number two, what you can get from it is that the relationship is negative, and since it is 0.16, then it is quite low correlation, right? Just remember the Cohen's criteria that we had discussed, the cutoff values. Minus 0.62 or negative 0.62, that's an inverse correlation, and the effect size, the strength of association is quite strong. The cutoff was 0.5 or 0.64, strong according to Cohen's criteria. And same for gender, quite strong, right? And all of these are statistically significant. So we reject the null hypothesis because p-values for all the predictors is less than 0.05. Now, collinearity statistics, tolerance and variance inflation factor, they are for looking at multicollinearity, that these variables are not strongly correlated. VIF value ranges between 1 to 10, and if the value is greater than 5, and there are other cutoffs as well, other recommendations as well, but generally if it's higher than 5, according to some of the guidelines, then the variables are strongly correlated, and that would make your regression model invalid. But that's not the case with us. So none of these variables are strongly correlated. So this is really the output for regression analysis. And just to cover this, we had to go through a lot of theory, but you would recognize that that theory was really essential to understand and run regression analysis in SPSS or any other statistical software for that matter. I would like to acknowledge these references. That's where most of the scatter plots came from. I would recommend everyone should buy a subscription for statistics.layer.com because they have detailed guides for running different tests on SPSS. And it's quite beneficial and enough to master statistical analysis for at least undergrad and even at master's level research and even in Western countries, really. YouTube tutorials for marine stats, really good. And then Essential Medical Statistics. It's a statistics book by Betty Kirkwood. It was written by Betty Kirkwood and her colleague Stern, and they teach it to master's students in London School of Hygiene and Tropical Medicine. So it's a really good reference book to have and learn statistics from. So open to discussion, and it was quite a lengthy lecture, and yeah. What Cook's value? So we have a question that says, what Cook's value will be significant enough? So I'm just going to take you through that slide of mine. So we have outliers and influential points. So leverage values less than 0.2 is safe. Cook's distance greater than 1 should be investigated. And case-wise diagnostics plus minus 3 cutoff, whether residual might be an outlier or not. Any other questions, or if someone would like to discuss it? So it's really still an introductory lecture, and there is a lot of things that you can cover. But I think this would give you a really good primer if you want to understand more complex concepts. Because these regression models, all of these concepts to extend to more advanced models of logistic regression, generalized linear regression, to generalized estimating equations and longitudinal models. These concepts extend to all of those statistical techniques. So no more questions. I'm just going to stop sharing. So statistics can be quite boring, but if you do it with case studies and you have your own data sets to play with, then it becomes really quite pleasurable activity. But the only criteria is you collect your own data and try to play with it.
I think Iman has probably stepped away from his desk. So I would like to wrap up. Thank you, Dr. Vakas, for joining us in this lecture. It was quite comprehensive, as much as it can be in 90 minutes. And I think I learned a lot along the way. Thank you for all those who joined for this session. With this, we'll wrap up. We'll have the recording available, and I will share on the WhatsApp group and other areas too. I was looking at the statistics.lear.com's access. I know when it translates into dollar amount, rupee amount, it can sound pretty expensive, but for example, the year access is only $20, which is